For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. Problem 1. A planar layer of insulating liquid having a mass density Ps has the equilibrium thickness d. The layer separates infinite half-spaces of perfectly conducting liquid, each half-space having the same mass density P. The interfaces between insulating and conducting liquids each have a surface tension Y, but Ps is sufficiently close to P so that gravity effects can be ignored. Voltage applied between the conducting fluids results in an electric field in the insulating layer. In static equilibrium, this field is E0. Determine the dispersion equations for kinking and sausage modes on the interfaces. Show that in the long-wave limit KD1, the effect of the field on the kinking motions is described by a voltage-dependent surface tension. In this long-wave limit, what is the condition for? Problem. Voltage-dependent surface tension. In this long-wave limit, what is the condition for incipient instability? Problem 2. A vertical wire carries a current I so that there is a surrounding magnetic field. A. In the absence of gravity, a static equilibrium exists in which a ferrofluid having permeability 1 forms a column of radius r coaxial with the wire. The equilibrium shown in Figure 8.3.2b approaches this circular cylindrical geometry. Show that conditions for a static equilibrium are satisfied. livexamhelper.com. B. Assume that the wire is so thin that its presence has a negligible effect on the fluid mechanics and on the magnetic field. The ferrofluid has a surface tension Y and a mass density much greater than that of the surrounding medium. Find the dispersion equation for perturbations from this equilibrium. C. Show that the equilibrium is stable provided the magnetic field is large enough to prevent capillary instability. How large must HO be made for the equilibrium to be stable? D. To generate a significant magnetic field using an isolated wire requires a substantial current. A configuration that makes it easy to demonstrate from a conventional loudspeaker. A cross-sectio of such a magnet is shown in Fig. P8.11.1. In the region above the magnet, the fringing field has the form /r ferrofluid placed over the gap will form an equilibrium figure that is roughly hemispherical with radius r. Viewed from the top, each half-cylindrical segment of the hemisphere closes on itself with a total length r. For present purposes, the curvature introduced by this closure is ignored so that the axial distance is approximated by z with the understanding that z equals 0 and z equals k are the same position. Effects of surface tension and gravity are ignored. Argue that the m equals 0 mode represented by the dispersion d magnetically consistent with this revised configuration. livexamhelper.com. E. Show that, in the long-wave limit KR1, the m equals 0 waves that propagate in the z direction around the closed loop of ferrofluid do so without dispersion. What is the dispersion equation? F. One way to observe these waves exploits the fact that the fluid is closed in the z direction, and therefore displays resonances. Again, using the long-wave approximations, what are the resonant frequencies? How would you excite these modes? Problem 3. The planar analog of the axial pinch is TH sheet pinch shown in Fig. P8.12.1. A layer of perfectly conducting fluid, which models a plasma as an incompressible inviscid fluid, is in equilibrium with planar interfaces at x equals +d/2. At distances a to the left and right of the interfaces are perfectly conducting electrode that provide a return path for surface currents. livexamhelper.com. Which paw vertically through the fluid interfaces. The equilibrium magnetic field intensity to right and left is HO, direct is shown. Regions A and B are occupied by fluids having negligible density. A. Determine the equilibrium difference in pressure between the regions A and B and the fluid O. LiveExamHelper.com. B. Show that deflections of the interfaces can be divided into kink modes and sausage modes. C. Show that the dispersion equation for the kink modes is with K, while the dispersion equation for the sausage modes is D. Is the equilibrium, as modeled, stable? The same conclusion should follow from both the analytical results and intuitive arguments. At equilibrium, a perfectly conducting fluid, plasma, occupies the annular region R less than A Fig. P8.12.2. It is bounded on the outside by a rigid wall at R equals A and on the inside by free space. Coaxial with the annulus is a perfectly conducting rod of radius B. Current passing in the z direction on this inner rod is returned on the plasma interface in the z direction. Hence, so long as the interface is in equilibrium, the magnetic field in the free space annulus B less than R is. Problem 4. LiveExamHelper.com. A. Define the pressure in the region occupied by the magnetic field as 0. What is the equilibrium pressure 2 in the plasma? B. Find the dispersion equation for small amplitude perturbations of the fluid interface. Write the equation in terms of the functions f, a, and g, a, o, the. C. Show that the equilibrium is stable. Problem 5. A perfectly conducting incompressible inviscid liquid layer rests on a rigid support at x equals b and has a free surface at x equals e. At a distance above the equilibrium interface y equals 0% ISA high and con DUC SISEE for HDAV I 1.14 ing EUF conductivit y as. This sheet is backed by infinitely permeable material. The sheet and backing move in the y direction with the imposed velocity u. With the liquid in static equilibrium, there is a surface current Kz equals HO in the conducting sheet that is returned on the interface of the liquid. Thus, there is an equilibrium magnetic field intensity I equals hot in the gap between liquid and sheet. Include in the model gravity acting in the x direction and surface tension. Determine the dispersion. LiveExamHelper.com. For temporal or spatial modes. Problem 6. In the pinch configuration of Figure 8.12.1, the wall at R equals A consists of a thin conducting shell of surface conductivity surrounded by free space. A. Find the dispersion equation for the plasma column coupled to this lossy wall. B. Suppose that the frequencies of modes have been found under the assumption that the wall is perfectly conducting. Under what condition would these frequencies be valid for the wall of finite conductivity? C. Now suppose that the wall is very lossy. Show that the dispersion equation reduces to a quadratic expression in JW, and show that the wall tends to induce damping. LiveExamHelper.com. Solution. Solution 1. Figure 1. A planar layer of insulating liquid separates infinite half-spaces of perfectly conducting liquid with the designations indicated in the figure. First, consider the bulk relations. The perturbation electric field is confined to the insulating layer, where the transfer relation for the mechanics are applied 3 times. Perhaps it is best to first write the second of the following relations, because the transfer relations for the infinite LiveExamHelper.com.